Okay, exam one, walking through just the problem statement, the control variable is x, which is the outlet mass fraction. The system is designed to keep that constant. The manipulated variable is W2, which is the flow rate of stream 2. The controller adjusts the valve to control that flow. And the disturbance variable is x1, which is the inlet mass fraction of stream 1. The problem states the system must handle potential variations in that stream. And the next part is part D. We're deriving the first order process and disturbance transfer functions using these two and calculating for these values. We're starting with the dynamic mass balance, and then we're linearizing and simplifying that and taking the Laplace, which gets you this guy. And then we're separating this into the disturbance and process variables to get into the k over like tau plus 1 format. And then, so the Kp ends up being the process K value, and Kd is the disturbance. And we can solve for that. And Kp ends up being 1.79 times 10 to the negative fourth minutes, and then Kd is 0.685. There are no units there. Tau ends up being 13.41, which you get from here, which is m over W1 bar plus W2 bar. M is the kilograms. You have to solve for that separately, starting with the area and then having volume times density. The next part is part F. We're tuning the PID controller using the internal model control relations. Renewing the process with a dominant time constant is recommended to set tau c equal to 1/3 of tau dom. We solved for tau dom earlier. That was at 13.41 minutes. Take 1/3 of that, you get 4.47 minutes for tau c. To find k total, you multiply all of the k values together. You're going to be getting 0.134. To find g total, you do this exact same thing with the g values, except for gd is not in the loop, so we're not including that there. A lot of the g values are actually found up here, but that was in class portion, so I'm not going to go over that. But that ends up getting you the k total, e to the negative theta s, all over tau v s plus 1 multiplied by tau s plus 1. And that is case I in the handout. And then we can use table 12.2 to figure out the format for that and the format for these guys to plug into this one. But tau d ends up being 0.710 minutes, kc is 16.3, and tau I is 14.16 minutes. And the last part for the screencast is the two homework problems. The first one is describing CO2 effluent with ammonia in the stir tank heating system. This is the problem statement for the first one. That's the little picture, variable information. Walking through the homework solutions. The controlled part is CCO2. Manipulated is QA, that's the ammonia flow. And the disturbance value is QF, which is the feed flow. This is a feed forward problem. It's measuring the disturbance and acting before it affects the output. We're modeling relationships between KD and KP. KD is the effect of QF, and KP is the effect of QA. And the goal is for CCO2 to go to 0. You don't want it to change. So based on like the problem statement, we can build um, our little block diagram from here, and then we can solve for part B and finding G of F, which ends up being 0.350. And then the last part, we have 16.5, which is a stir tank heating problem. We're wanting to control the for the final temperature, which is T2 down here. Yes. This has the controllers also listed into it based off of this thing. Um, and we're adjusting the T2 is adjust the set point, which is T1 SP of the T1 controller. It's the output signal and is added to the output of the feed forward control. That it's a cascade control system with a feed forward controller being used to help control T1. And this is the block diagram for it. So you can see both the outer cascade control and the feed forward both being incorporated into that loop. Yay. Bye bye.